So we're continuing with biotechnology. In the last section we talked about pedigrees, which are basically a family tree, but instead of looking just at the names, they look at traits that an organism has. And now we're really starting to move into the technology that we can use to possibly understand those traits a little bit better. One of the things that we can use is a DNA fingerprint. It's a unique band pattern made of DNA fragments. Now this is what is interesting, is this part about fragments. Why would our DNA be in fragments? Well, we do have to specifically cut the DNA into pieces. We do that on purpose because just looking at your DNA, remember everybody has double-stranded DNA. And so I can't really see much difference between you and me if I just look at DNA. But if I open the DNA up and I cut it into pieces, my pieces will be cut differently than your pieces. And so this is kind of what a DNA fingerprint looks like. It's a banding pattern. You can see that this person has a different set of patterns than each of the other people on here. Suspect 1 and suspect 2. Now we have crime scene 1 and crime scene 2, and we look at where the DNA at the crime scene came from. So if I have DNA at a crime scene, I can get the DNA from my victim and from my suspects, and I can figure out which suspect was probably at that crime scene. So we can use it for violent crimes, or we can use it for paternity. Paternity is used to determine the father of a child. Usually we know who the mother is because she physically gave birth to the child. But sometimes if children are separated from their parents, like during a natural disaster, or if they were adopted, sometimes we need to use it to figure out both parents as well. But the big thing to know is that it's made of DNA fragments, of pieces of the DNA. And so we're going to look next at how exactly you make a DNA fingerprint. You use something called a gel electrophoresis. Gel electrophoresis. It's the tool used to create a DNA fingerprint. It separates pieces of DNA based on size. And so how exactly do we do that? Well, the first thing that we do is we use a restriction enzyme. A restriction enzyme cleaves or cuts. The word cleave means to cut. Cleaves the DNA sample at a specific sequence. For example, maybe between a T and a C. And so restriction enzymes cut the DNA between the nitrogen bases. You can see here in this picture that we have on the board here that we're going to be cutting this enzyme, EcoR1, cuts here between the two Gs. So let's write out an example. Let's say that we have someone whose DNA is AAT, CCG, TTA. Okay? And if there is a restriction enzyme that cuts, that finds AAT and cuts between AAT and CCG, that's where the enzyme cuts. Well, if someone else's DNA is AAA, CCG, TTA, then their DNA won't be cut by that restriction enzyme. So because the restriction enzyme cuts at a specific sequence, this is how different people or different organisms, we can use DNA fingerprints to look at bacteria. For example, when they want to know what's causing an outbreak, like a flu outbreak, they'll use DNA fingerprints to test the DNA of the virus or of a bacteria. It's how different organisms' DNA is different sizes. Different size pieces. Because that enzyme cuts at only exactly certain spots. If your DNA doesn't exactly match up, if yours wasn't GAATTC but instead it was GGATTC, it wouldn't get cut there. So mine might get cut into two pieces, yours might not get cut at all, and then when we create the DNA fingerprint, we'll be able to see the differences there. So the first thing we have to do is cut the DNA with a restriction enzyme. Then the fragments are loaded into a gel. Now we do want to notice that this gel is going to be difficult to move through. It's kind of like Jell-O. It's not a solid, but it's not a liquid. When we add electricity to it, the electricity forces the DNA fragments through the gel. So we have these little pieces of DNA that we put inside of a gel here at the negative end, and then we add electricity to it, and the electricity pushes the pieces through the gel. Now as those pieces are moving, we've got some big pieces and some little pieces. So a good example is, if I take a bowling ball and a tennis ball, and I push them with the same force, which one will go further? I'll be able to throw the tennis ball further because it's smaller and it can go faster. And so that's exactly what happens with our DNA fingerprinting, is when we add the electricity pushes the smaller pieces further, and that's how we end up with some pieces at the bottom and some pieces still at the top. Now the bands here that you see, they look like they're the same size, but that's just because there were that many pieces that were that length. And so this is what creates a DNA fingerprint. And so you can see again here, we take our DNA sample and cut it with restriction enzymes into smaller pieces. We add the pieces to the gel. We add electricity and the pieces move through the gel. And then we end up with a banding pattern where we can see that the smaller pieces move faster and further than the bigger pieces. And this is what a gel electrophoresis or DNA fingerprint really looks like. And so we're going to stop here, and we'll come back to genetic engineering later, because genetic engineering is how we use DNA to actually possibly change our traits. But this is where we're stopping for now.